All right, so today what we're going to be doing is just moving forward. We're going to extend just the concepts that we've had up to this point for derivatives and really just look more specifically at logarithmic functions. The following section after this will be looking more at exponential functions and how to take derivatives. What's really cool about both logarithms and exponential functions is the derivatives are relatively simple. More simple than some of the properties that you probably have looked at up to this point. And what I'm going to do, I'm just going to go through these notes and then we'll go through just a slew of examples to hopefully explain how all of this works. The one thing that's really important to recognize is that the logarithmic function, understanding conversions between logarithmic and exponential functions is really kind of key. Because it can really alleviate many problems that you face when you're looking and taking derivatives. You're looking for slopes of tangent lines, rates of change, that sort of thing. So understand this property is really helpful. The derivative of a simple natural log, we're mostly going to be focusing on natural logs, not really looking at logs with just a different base. I'm going to focus mostly on natural logs. When we take the derivative of a natural log, it's just going to equal 1 over whatever was sitting inside that natural log, so the x, in this case, 1 over x. The chain rule is kind of a nice application of this because suppose that u is a function, okay? In this case, it's a differentiable function of x. The derivative of this thing is simply just 1 over whatever that function is times the derivative of that function. So in a similar sense, kind of like when we do, like when we have a polynomial raised to a higher power, right? So say we have like 2x plus 1 to the 4th power. We would treat the 2x plus 1 like the u, and then we would take the derivative of u to the 4th. So that would be 4u to the 3rd. Right? And then we'd multiply it by the derivative of u. So in a sense, that's kind of what we're doing here. It's the chain rule application applied to this. And that's really kind of the extent of what we're going to be doing. I do want to point something out really quick. If you're needing some assistance, go back to some of those early sections of material that we did when we looked at logarithms. And part of the reason why I suggest that is because taking derivatives of logarithms, especially when you've got complex functions kind of baked inside of those logarithms, can be really complicated and challenging unless you know the properties. Because if you know the properties, then you can separate logarithms out into multiple logarithms, and taking derivatives is so much easier. So we'll see some examples kind of where that happens, but I do want to just encourage you to do that if you need the help. All right, so let's go ahead and go to our whiteboard here. We're going to look at a few problems. Man, I got quite the cough today. Sore throat. It's not really sore. It's more like a frog in there or something. Take a drink of coffee. That'll help. All right, so let's go ahead and take a look at a few problems. So this very first one, okay, suppose I've got f of x is equal to 4 natural log of x, okay? So on this particular problem, what we're going to do is we treat this like they're multiplying. Anytime you've got a coefficient out in front of something, you don't really have to treat it as though it's a separate function. Technically it is, but it's really just a coefficient because the derivative of it is 0. So even if you did apply the product rule, you'll see that 1/2 of that product rule is just going to pretty much get thrown out. So when we do the derivative, you can just treat the coefficient just like it's part of, it's like just a number kind of tied to the natural log. So the derivative of our natural log of x is just going to be 1 over x. So we've got our 4 times 1 over x, which in this case is going to be 4 over x. Okay, and that's our derivative. That's pretty much it. All right, let's do another one. I'm going to do this next one in 2 different ways, actually. So here's our natural log of x to the 4th. Okay, Now there's two things that I specifically can do. The first is I could just treat this as the same thing as 4 natural log of x, which is basically the same thing as the very first question we looked at. And the reason why is because, again, reminder, that exponent tied to the function, it can come down in front as a multiplier, and so as a result, it just changes the complexion of the function, even though it's identically the same. So when you take the derivative of this, it's going to be much easier, right? It's literally just going to be the same thing as 4 times 1 over x, which is 1 over 8. 1 over x, I don't know why I did that, which is the same thing as what we just got on the, I almost did it again, geez. Okay, 4 over x, there we go. If I do it the traditional, so like without utilizing the property, okay, so I'm just going to come over here and treat it like I didn't do anything. Natural log of x to the 4th. So this is where that chain rule comes in. So this thing right here, I can treat it as though it's u is x to the 4th. The derivative of u prime, is 4x to the 3rd. So if I use the chain rule, say y is equal to natural log of u, then the derivative is equal to u prime times 1 over u, which in this case is going to be 4x to the 3rd times 1 over, my u is x to the 4th, okay? And then you can see what happens here. I get 4x to the 3rd over x to the 4th. This 3 cancels with 3 of those, and I'm left with a 1. So this whole thing goes away, and I'm going to be left with 4 over x. Okay. Again, it's way more complicated, and that's kind of the point. I'm trying to illustrate to you how this can become a bit of a nightmare. And again, this is a simple, I mean, relatively simple problem. It's not challenging compared to many of the other ones that we're going to see. So, yeah, it's good to really know those properties. All right. Let's go ahead and jump to the next problem. All right, so this next problem that we are going to look at, this is definitely one that's going to require the use of the chain rule. So we've got y is equal to natural log of 6x plus 1. Okay. And again, every single time we're using the chain rule, we're just looking specifically at this thing, okay? So we'll set u equal to 6x plus 1. And it's kind of nice to get into a habit of actually writing this out, because in some other, when we start getting into antiderivatives or integration, we're actually going to be doing a lot of this. So if u is equal to 6x plus 1, the u prime is going to be 6, okay? So that means that my derivative here is going to be u prime times 1 over u, which in this case is just going to be 6 times 1 over 6x plus 1, which is the same thing as 6 over 6x plus 1. So that's pretty much it. You take the derivative and you multiply it by just 1 over whatever that inside stuff is, okay? I'm probably not going to write out this step next time in between. I'm just going to assume that you know what that is. There's a really detailed explanation of why that works the way it does in the textbook, so if you want to go ahead and look at that, you certainly can. But I'm not really going to go into all the nitty-gritty details. All right, let's go ahead and take a look at this next one. Suppose I've got y is equal to the natural log of 8x cubed, excuse me, minus 2x, okay? So I'm taking the logarithm of all of the stuff on the inside. Notice I can't, utilizing the properties of logarithms to kind of separate stuff out, it really only works when you have like multiplication and division going on in between. In this case, because I've got a subtraction sign, I can't do anything. So So let's go ahead and kind of treat this one. So I'm going to let u equal 8x cubed minus 2x. The derivative of this is going to be 24x squared minus 2. So that means that my derivative, you're probably wondering what happens to that minus 2x. That we just do the derivative of that completely separately because it's not connected to a logarithm. So here we're going to have u prime, so 24x squared minus 2 divided by my original 8x cubed minus 2x. And then I'm going to subtract off the derivative of that 2x, which is just the 2. Okay. All right, this is one of those next ones where they're asking us to find the derivative. So in this case, find ds dt if s is equal to natural log of t cubed times t squared minus 1. Okay. So let's use the properties of logs here to separate it. So we've got s is equal to, notice how these two things, I mentioned it just in the last problem, but when you've got multiplication connecting these two things, you can separate them out as different logs, but just adding. So here this is the same as natural log of t cubed plus the natural log of t squared minus 1. Okay? And even further, this first one that you see here, because there's an exponent tied to that t, we can bring that down in front as a multiplier. And then this is what we're going to have on the back end, t squared minus 1. There's nothing we can do with that. That's just going to be whatever it is. All right, so if we take the derivative, s prime, or in this case, they're saying ds dt, it's the same thing. Okay, ds dt, which is s prime, this is the same as 3 over t for the derivative. And then for the derivative of this, we're going to add, remember the derivative of the inside. So now I'm going to try to do it without writing the whole thing out, okay? The derivative of the inside, 2t, divided by my original, t squared minus 1. Okay, and that's it. Now, they may, I don't know if they would ask this on a homework question, but they might want you to find common denominators. And so it would be what? Let's take a look. I would have to multiply this times t squared minus 1 all over t times t squared minus 1 plus 2t times t. T squared minus 1 times t. Okay, this is the common denominator part, and then you're going to get 3t squared plus 2t squared. 2t squared minus 3 divided by all this stuff, t times t squared minus 1. And that you'll see is equal to 5t squared minus 3 divided by t times t squared minus 1. Okay. Now, I kind of did that for a reason, because ultimately, I feel like I did something wrong here. T squared. Oh, it's t cubed. What am I doing? Wait, hang on. T squared. Nope, that works. Yep, so there it is. Okay, we'll just leave it at that. I don't want to get too complicated here. All right, let's go ahead and take a look at, suppose I don't do this using the derivative or separating it out, okay? It's kind of like what we did earlier in the problem or in the section. So let's go back to my original. S is equal to natural log of t cubed times t squared minus 1, okay? So you'll see right? If we use the chain rule, we have to do the derivative of all of that junk on the inside divided by the original, okay? But notice the derivative of all this stuff on the inside is actually a product rule. This is kind of what I was saying. It gets really complicated and annoying. But so here's what it would be, okay? We would have u prime over u, which in this case, if u is equal to all that junk, so let me go ahead and just write it out, t cubed, t squared minus 1. We'd have a product rule on the top because we've got this function times this function, so that means that we would have the derivative of the first times the second, t squared minus 1, plus the derivative of the second, which is 2t, times the first, t cubed, okay? So there's our product rule, and what I want to do now is simplify this thing out, because you're going to see something really cool happen. 3t squared times t squared is going to be 3t to the fourth. This is going to be minus 3t squared. And then we're going to have plus 2t to the fourth, all divided by t cubed times t squared minus 1. Okay? And you can kind of see it looks really similar to the previous part. So let's just combine our like terms. We've got 3t to the fourth, 2t to the fourth, so that's 5t to the fourth. I've got a minus 3t squared all over t cubed, t squared minus 1. And notice what happens. I can factor out a t squared in both the numerator and denominator. So this is going to be 5t squared minus 3 divided by t squared times t squared minus 1. Okay, and then this thing cancels with that thing, and notice what I get as a result. Okay, it's literally the exact same thing. So again, it's possible to do it multiple ways, but this way is just way more complicated. In my opinion, I guess it's kind of an opinion thing, but in my opinion, it's more complicated if you don't separate it right off the get-go. You're looking at much more complicated derivatives. Like this next one. It's fancy me saying that because it works out that this next one is really annoying as well. Let's do dy dt if, so we want to find dy dt if y is equal to the natural log of t cubed plus 3 divided by the square root 1 minus t. Okay, that's all in the same natural log there. All right, so let's go ahead and I'm not going to show you the way to do it without doing a natural log because you've got a chain rule, like a power rule kind of applied here, and a quotient rule, and it's just super annoying. I'm not going to even attempt to do that because it's just a waste of time at this point. Hopefully you're catching my drift and seeing that it's good to just convert these as easily as possible into something that's much more easy to work with. Okay, so because we have a division, this thing is going to be subtracting. So we've got t cubed plus 3 minus natural log square root 1 minus t. But notice the 1 minus t, that square root is the same thing as to the 1/2 power. Okay, so this is a natural log of t cubed plus 3 minus natural log of 1 minus t to the 1/2. And that 1/2 as an exponent can actually come down as a multiplier. So we've got natural log t cubed plus 3 here minus 1/2. That's a half. Natural log of 1 minus t. Okay. So now doing these derivatives is a lot more straightforward, I think. dy dt. So we'll do one piece at a time. Again, like kind of think about that minus sign as separating the two completely out, so you don't have to worry about any kind of quotient or product or anything like that. It's just the derivative of this thing, in this case subtracting the derivative of that thing. So the derivative of this is the derivative of the inside, 3t squared, and we're dividing by the original, t cubed plus 3. Over here, the 1/2 is going to come along for the ride, and we're going to multiply that by the derivative of this, which is a minus 1, divided by 1 minus t. Okay, so now I'm not going to find common denominators here. I just wanted to point that out. But let's just go ahead and simplify real basically here. That's a cubed plus 3. This will be a plus 1 over 2 times 1 minus t. Okay, and there it is. That's our solution. So this right here is the derivative of all that crazy nonsense up there. So yeah, it's really helpful to know those properties and just to be able to utilize them at a moment's notice. A lot of it really just comes down to practice too, so if you do need extra practice, I would suggest going back to those sections of material, reviewing the video, and when you're going through the video, my suggestion would be I generally will write the problem down, pause the video, and try to figure it out on your own, and then just watch me as I go through those problems. So that helps you kind of build like I guess your confidence as you approach those problems. Just to compare and contrast, you can kind of see the process play out. All right, let's do this next one. So I need to find the derivative of this. Natural log 3x plus 1 to the 1/2. Okay. And again, because we're dealing with natural logs, that exponent can drop down in front as a multiplier. So this is the same as 1/2 natural log 3x plus 1. And now when I do the derivative here, y prime, this is going to be the same thing as what? So 1/2 times, we've got the derivative of this, which is of 3x plus 1 is going to be 3. And then the original, okay? So now I've got 3 up top, 2 times 3x plus 1, and if you want, you can multiply that all out. Doesn't really mind. Like, I don't really care either way. I mean, I guess let's just do it. 6x plus 2. There we go. So there's our solution. Okay. All right, on this last question, we need to find the relative max and the relative min. So this is kind of looking back at a few sections of material. The process is identical. We're just introducing or utilizing logarithms, in this case, to find the slope of the tangent line. So, or setting the slope of the tangent to 0. So let's go ahead and take a look. So suppose I've got y is equal to x squared minus 8 natural log of x. They were so nice to put that 8 down in front, so we didn't even have to waste a step doing it. All right, so let's go ahead and do the derivative. So the derivative of this is 2x. The derivative of this is going to be minus 8 over x. Okay. And then what we'll do is we'll set this equal to 0. So 0 is equal to 2x minus 8 over x. And if you're wondering how to solve this, what I would do is I would bring the 8 over x to the other side. This is the same thing as that right there. And then just cross multiply. So as a result, you're going to get 2x squared is equal to 8. X squared is equal to 4 if you divide by 2, which means that x is going to equal plus or minus 2. Okay. So let's check for the y values. If I've got x is equal to a minus 2, y is going to equal what, 4 minus 8 natural log of minus 2. Uh-oh, that's a problem. Okay. This right here does not exist, okay? So you cannot take the logarithm of a negative number. It has to be positive. They're not defined, so it doesn't exist. If I do it with the positive, I'm going to get y is equal to 4 minus 8 natural log of 2, which does exist. And so we're in good shape. So this is the relative, well, maybe relative maximum. I don't know. Let's actually go to Desmos and take a look. Let's see here. Come on, there we go. Okay. Graphing calculator, and then we'll do, so we'll do the original function here, which is y is equal to x to the 2, and we're subtracting off 8 natural log of x. Okay, so you can see that here we've got it looks like a parabola, but there's a little bit of stuff going on with that natural log. The minimum is going to be at x is equal to positive 2, and you can see that there is nothing to the left of this axis. It just gets really, really, really close. So that minus 2 just doesn't even exist. So it's positive 2, and then at minus 1.545. So that's going to probably, well, whatever 4 minus 8 natural log 2 is going to be that. So that's how you go about doing that problem. How about that? All right, well, that's pretty much all I had. Let me go back to the notes here really quick so you can kind of see it if you need it. So if you have any questions, feel free to let me know, and I hope you have a fantastic day.